There's two videos I'm going to post based upon the discussion thread about how we solve problems in schools. And this one has to do with picking the right kind of data. The other one has to do with why we actually need to do some kind of test in the first place. So to begin this discussion, I'm going to show you this example where we have people that are completing a job scale. And you've seen something like this before, where you're asked to complete something on a scale of 1 to 5 or 1 to 4, where 1 is strongly agree and 5 is strongly disagree. That actually is taking this scale, where these words are sitting there, we're changing them to numbers. That's not the same thing. Remember, this is the basis of our scale. We converted it to this out of convenience. So hypothetically, in this situation, we asked participants to complete the first survey, and we asked them to put gender on there as a variable. We're used to seeing surveys like this, where the words strongly agree are replaced by numbers. It measures a single construct. We want to know for each of these participants what scale number best represents their personal view of their job involvement. And most people are used to taking surveys like this, and what you do, as you all know, is you take those 12 responses, those numbers, add them up, divide by 12, and that gives you a single participant score. And then we can take everybody's score and compare those. That's where the mistake generally occurs. Remember that we transformed these words into numbers and used those numbers as placeholders. We did that. No, I don't want to do that right now. Sorry about that. We use those numbers as placeholders. And we did that because it makes it easier to look at the information and people are more comfortable with the numbers. If you look at the survey, it's exactly the same thing. We just left the letters in there. And those letters are just the words that were left. When we took them out, we just replaced them with the letters because the words take up too much space. If we used the second survey and we wanted a single indicator, the best representative participant, we could have two options. We could choose the median, the one in the middle with all the responses ordered, or the mode, the one that occurred the most. We cannot average the letters of the words, and everybody knows that. We've known that since third grade. You can't add words together and divide by how many words you have and it tell you anything. You have to use a different measure of central tendency. Now, theoretically, this should force us to recognize that numbers are not always numbers and should not be treated as such, but it doesn't. More often than not, researchers continue to treat the placeholders as numbers and continue to calculate inferential statistics. That's the second mistake, because inferential statistics, what we're going to be talking about somewhat in this class, and you'll actually be doing it in one of the other research classes later on, can be divided into two categories depending on the type of data that you have. Gaussian data, that means Gauss was a mathematician that developed the normal curve. And we use inferential statistics, parametric statistics, when it is a normally distributed set of data, or it's represented as ratio data, meaning that it's really numbers. For example, money, temperature, how many times something occurs, speed. Those are real numbers. Non-Gaussian data is data that's not distributed along a normal curve. So if you don't have a large enough group to say that you can take a sample to represent a population, well, then you don't have a normal distribution. There's nothing wrong with that. That happens. But this also, sorry, that's my cell phone, happens along with rank or ordinal data. And what I mean by rank data is, did you finish first, second, third, fourth, eighth, 100th? Or ordinal data means it is categorical. That's survey data. Strongly agree, disagree. And those fall under a group of tests called non-parametric statistics. Those two types of groups, the parametric and non-parametric, test similar questions, but they require different analysis. So for example, we can compare two groups. In this case, we want to compare the males and the females and their responses. How we do that depends on the kind of data we gather. So in this example, we asked the males and females to complete a job involvement scale. And for argument's sake, we're going to run a test to compare males to females on their level of responses, because hypothetically we want to know if there's a difference. We enter scores, we enter each individual score, both male and female, in a database called SPSS. With a few punch of buttons, miracle occurs, and we get these results here. So males is 1, female is 2. There's 19 males, 17 females. This is their mean score. Remember, I'm doing this with a arithmetic mean. Here's the females. So there's all that data there. There's standard deviations associated with that. And what we're going to see down here is the result of something called the independent t-test. An independent t-test is a parametric test for comparing real numbers. So without going into great detail about it, because that's for a different class, we want to know if there's a significant difference in the scores between the males and the females. Our results tell us that there is not, because this number is not less than 0.05. And basically what that means is there's too much overlap between the males and the females in terms of their scores. So we'd say that no, there's no difference between males and females. Now let's assume for just a minute that we do this right. Let's assume that we didn't average everyone's score and only use mode as the best representation of a measure of central tendency. So we employ a different test called a Mann-Whitney U, a non-parametric version of an independent t-test, to determine the difference between these two groups using ordinal data, Likert data, what the strongly agree, etc. The first table shows something called mean rank. And the computer puts the scores 1, 2, 3, 4, 5 next to male or female, and then determines if more males have 1 and 2 than females who might have more 2s and 3s. What we want to know again is there a difference in the ranks depending on whether these are males or females. So again, this isn't where we're going to do this, but down here what we see is there is a significant difference because that value is less than 0.05. Here's a rub. Why is this important? If we're making a policy decision based on the outcomes of involvement and we're worried about gender as an issue, there's a difference in the answer depending on whether we use the right test or the wrong test. If we use the wrong test, we say there is no difference between males and females. No need to change the policy. If we use the right test, we get a very different answer indicating a difference in male and females. So we've made a mistake. We've made a type 2 error, meaning that we failed to say the right thing. Yet we're going to make a policy decision about that. That's why what you learn from this is really, really important, is because it does make a tremendous difference in terms of the outcome. A lot of people understand that and realize it, but yet we still continue to do the wrong thing. The other thing that I want to show you is another example where we're doing the same thing with years of experience. So on here we have 0 years of experience and 1 year of experience. And we had everybody complete the job scale, and there's a couple of things that happened here. This column is we left everything where it is not rounded up. So I want you to notice there's only 2 scores that we didn't round it up. And if you round up, that is a conscious choice on the part of the researcher to do that. This is where we did round up. So again, there's only 2 places where that mattered. This column is each respondent's score, but we used the median. meaning we didn't take that data and convert it to numbers. We just left it alone. So here's what I want to show you. In the first example, where we did round up, we get a mean, standard deviation, and we discover that there is no significant difference because that value is not less than 0.05. If we don't round up, I want you to see what happens. Simply making a decision, a mathematical decision or a choice to round up or not round up, changes the answer. Here we had no significant difference. Here we did. That matters tremendously. The last column, where we had the medians, and again, this was this person's score by doing it the wrong way, the right way. We discover there is a significant difference. So I've run this same set of data 3 different ways. I did it the wrong way, a kind of wrong way, and a right way. Yet I got 3 different answers. So the point of this is not for you to understand t-tests and all that. The point of this is to understand if we use the wrong score, if we do this the wrong way, we get a different answer. Even if we make a subtle change about the kind of data that we're using in terms of we're going to round up versus not round up, it makes a difference in the score. The overall choice to use a parametric test versus a non-parametric test can have a policy implication, meaning that if you make a mistake, there's people that are going to make a decision based upon the choice that you make. So you've got to be able to choose the right thing. And the point of this whole course, along this point of this whole program, is for you to get better about making the right choice on the data and understanding that data well enough to explain it to other people about why we don't take this kind of score and treat it like they're numbers when they're not numbers. It's all the difference in the world.